We talked about gravitation as the force that dominates astronomy, but in most of our lives, gravitation of the Earth is important, but when we interact with each other or with objects around us, gravitation is completely unimportant. The gravitational force of a human being is negligible compared to the other forces we interact with. The force that turns out to dominate most of physics is electromagnetism, and so we need to understand some things about this. And the simplest version of electromagnetism is the force between two static charged objects. So there is in the universe a thing called electric charge. Some objects carry electric charge. You can charge your hair by combing it on a dry day. And the annoying force that makes your hair stand on end on a dry day is this electrostatic or Coulomb force, which has a formula that will appear familiar. The force between two objects of charges Q1 and Q2 is given by a constant times the product of the charges divided by the square of their distance. This might appear familiar. It's that square of the distance again. It's not exactly a coincidence. The big difference between electric charge and mass, or between Coulomb's law and Newton's law, is that Newton's law, remember, had F equals G m n over r squared, and these numbers were positive and the force was attractive, always. Gravitation is a universally attractive force. Coulomb interactions can be attractive or repulsive. It turns out that the force is attractive when the two charges are of opposite sign, so positive and negative charges attract, and charges of like sign repel with an equal magnitude, but the sign, the direction of the force, depends on whether the charges are equal or opposite. This in turn explains why this force does not dominate the universe and this force does. It's not because gravitation is stronger. In fact, we have an invariant measure of strength under which gravitation will be a far weaker force than electromagnetism. But because opposite charges attract, most objects are neutral. In the presence of charge, if you have something that's charged positively, it will attract negative charge until such time as it reaches equilibrium, in other words, is neutral. This is not possible for mass. There is no concept of negative mass. In fact, it's worse than that. We'll discuss the instability of gravity. This will have profound consequences, so I'm not just belaboring an obvious point. And charge, like mass, momentum, energy, etc., is conserved. You can neither create nor destroy charge, though, of course, charge can be transferred from one object to the other. So when you comb your hair, the comb is charged with one charge, your hair with the opposite charge. When atoms form an ionic bond, they exchange charges and so on. But the total charge in the universe, or in any enclosed region in the universe, is conserved. And then, you see, in gravitation, I kept wanting to talk not about the gravitational force, but the gravitational acceleration. So you talk about the Earth, for example, generating around it a gravitational field. The gravitational field is the statement that were a mass to be placed there, it would experience a force. And you can compute the force per unit mass without knowing what the size is of the mass that you would introduce. And in a similar way, you talk about an electric charge producing an electric field, which is the force per unit charge that would act were a charge to be placed there. So a charge creates an electric field around it, because another charge, were it to be brought there, would be affected, and a charge is affected by an electric field. It's worth getting familiar with these electric fields, so let's take a look at them. A similar phenomenon of a field, a region around an object in which other objects might be impacted, is encountered with magnets. A magnet creates around it something that we can call a magnetic field. In the presence of such a field, any other magnet, like this little compass, will align itself in a particular direction at any given point in space. Of course, it will align itself so that its north pole faces the south pole, and so on. And so we can imagine that this region of space has some property called a magnetic field, which is the statement that were you, remember there was a field here even before I brought the compass, that told you that were you to bring the compass, it would point in such and such a direction. Now, magnets and electricity initially appear completely unrelated, and it is known, however, that electric currents, in fact, produce magnetic fields. In the vicinity of an electric current flowing around a coil behaves very much like a magnet. We call this an electromagnet, and we see that we have a magnetic field in the vicinity of an electric current. Moving charges create magnetic fields. So this is the first relation between electricity and magnetism, but there is another relation, which is that if you have a changing magnetic field, it will cause charges to move so that this magnet has absolutely no impact on the charges in this coil. But if I move the magnet so that the magnetic field in the coil changes, then while the change is ongoing, current will flow, and current flows means there's a force on these charge carriers. This implies an electric field. A changing magnetic field causes an electric field, and I can, of course, cause the change by moving either the magnet or the coil. And so changing magnetic fields essentially can be thought of as generating electric fields. This has profound consequences. Let's see what they are. The fact that moving charges can create a magnetic field was discovered in 1820 by Ørsted, and it turns out that moving charges are also affected by magnetic fields. We saw that when we moved the coil in the presence of a magnetic field. Faraday realizes the phenomenon that we were discussing, which is that a changing magnetic field is tantamount to an electric field. 30 years later, Maxwell writes down what are the collected set of equations describing electric and magnetic fields, and in particular the phenomenon he needs to add is that a changing electric field creates a magnetic field. In the presence of a changing electric field, there's a magnetic field. And the combination of these two phenomena leads in Maxwell's equations as part of the solutions to propagating waves. Propagating waves in which essentially you set up a changing electric field which creates a magnetic field, which creates an electric field, which creates a magnetic field. You solve the differential equation that this leads to, and you find that it describes a propagating wave, and Maxwell computes from the properties of magnets and currents and Coulomb's law, properties that had been measured in the lab. He can compute the velocity of these waves that he's discovered, and their velocity, surprise, surprise, is precisely c. He didn't get it this precisely, but it coincides with the speed of light that Fizeau and Foucault had measured 11 years previously. So Maxwell has very good reasons to imagine that he's discovered that light is a wave, as Young said. In fact, we now know what it is a wave of. It's an electromagnetic wave. The disturbance that propagates in space when a light beam travels through it is an electromagnetic wave, is a disturbance in the electric and magnetic fields, which have come to take on sort of a life of their own. Remember, they were ways to calculate what would happen if you put a charge, and suddenly they create each other and they propagate through space far away from the charges that might have created them in the dim, distant past. They have essentially their own existence. And so we do talk about these fields as important objects. The understanding that light is an electromagnetic wave also tells you that you can, in principle, imagine oscillating a charge or creating an oscillating electric field at any wavelength or any frequency. So we know that we see light from between 400 and 700 nanometers in wavelength. What about the solutions to Maxwell's equation with wavelengths outside this region? And it turns out that there is an entire huge electromagnetic spectrum out there, ranging from, at very high frequency and very short wavelength, gamma rays with wavelengths of down to 10 to the 14, 10 to the 15 meters and below, except below that are very hard to produce, through the X-ray spectrum that runs from wavelengths of about 10 to the minus 9 to 10 to the minus 12 meters, and then the ultraviolet light, which is the chunk of the spectrum immediately beyond the deep violet light at 400 nanometers, that is the shortest wavelength our eyes can see. And then on the other side, to the left of the red light, we have infrared light, and below that, microwaves and radio waves, whose wavelengths can be hundreds of meters. And so there's this entire spectrum, and in fact we're familiar with it, we use it. Our eyes are sensitive only to this tiny little bit of the electromagnetic spectrum. Our eyes have all kinds of inefficiencies, but in this case, our eyes are well adapted to where we live. If you look down here at the bottom of this plot, this is the transparency of the atmosphere. And you see that, for example, gamma rays and X-rays are not very useful, despite Superman's claim to the contrary. X-ray vision is not very useful because X-rays are very quickly absorbed in the atmosphere. They do not penetrate. Visible light penetrates the atmosphere. A little window in the infrared penetrates the atmosphere. And then radio waves penetrate the atmosphere. Well, we know that because that's how we watch TV. But the wavelengths of radio waves are too long. You would need your eyes to be antenna. They would need to be on the order of meters in size. We do not have eyes meters in size. There would also be other limitations. It would be hard to see features of the universe smaller than a few meters across. So, given our need for fine resolution, our eyes are well adapted to the conditions under which we evolved. But the universe, on the other hand, produces light across the entire spectrum, from high-energy gamma rays to radio waves, and it's important, in order to collect information about the universe, to be able to observe it in all possible frequency bands. And indeed, with technology, people have developed ways to observe the universe in all of these frequencies. And at every time that we've developed a new technology and a new way to look at the universe, there have been new and often surprising discoveries made. Note that observations in many of these bands, in the ultraviolet, in X-rays, and in gamma rays, for example, need to be made outside the atmosphere. Putting a very good gamma ray detector on the ground will not buy you anything because gamma rays from space will not penetrate. So these observatories, including actually infrared observatories, tend to be space-borne, or at least high-altitude balloon flights. Radio telescopes can be placed on, and are placed on the ground. Those are these very large dishes that receive radio waves. And over the course of the class, we will have occasion to use information collected by all of these bands. So it's the richness of the spectrum corresponds to the richness of phenomena out there.